Okay, so I think this will finish our discussion of equilibrium, if you've been following through all along. So now we're going to talk about complex ion equilibria. We'll talk about what complex ions are and why those are important, but this will also be a chance for us to deal with reactions with large values of the equilibrium constant. That's going to provide different opportunities than what we've done before, which are small values of the equilibrium constant. Okay, first we need to understand what complex ions are, right? With some substances in solution, right? So let's look at something like a silver ion, right? If we have a silver ion in solution, there are some things that if you put it in solution with that, in this case, like ammonia, silver ions will react with two ammonia molecules to create an equilibrium. And so you get something with a formula 1 silver and 2 ammonia. But because the silver is positive and the ammonia is neutral, right? The sum of this is still positive. And so what we get is everything in this equilibrium stays in the aqueous phase, right? Now, right, there are several of these, right? So I can show a different one, right? So let's look at, right, if we've got aluminum 3 plus and 6 fluoride ions, that can make an aluminum fluoride. And if we add up our charges here, 3 pluses and 6 minuses add up to 3 minuses, and that then creates a complex ion where all of those things are in solution, right? That ion, because of its charge, water can interact with it and hold it in solution. And these ions that are made by the interactions of two things in solution to create an equilibrium are what we call complex ions, right? There's a good one, right? Let's look at, right, we'll go with iron, 3 plus, and a molecule called EDTA. I thought about drawing that for you, but I think it's probably a little more than we need to draw. But if you look on a lot of food products, you'll see, or cleaning products, EDTA in there, because EDTA makes strong complex ions, right, with metal ions in solution, and then holds them in solution, right? And so you see it in water softeners, in food products, in all kinds of things. And so we're going to get an iron EDTA complex, which has a 1 minus charge. But again, all of these parts will stay in solution, right? So there's one thing about complex ions, right? And there was one more I was going to show you, right? Because I thought it was sort of fun, right? Let's go zinc 2 plus 4 cyanide ions in solution will make an equilibrium, which is zinc cyanide, zinc tetracyanide, which would then have a charge of 2 minus aqueous, right? So that's what happens with complex ion formation, right? So complex ions themselves are an interesting chemical species. But complex ions are also useful because often, at least the ones that are most useful to us, are equations or reactions that have very large values of K. So for example, for this silver ammonia, the equilibrium constant for formation of that is 1.7 times 10 to the 7th. Right? The equilibrium constant for that aluminum fluoride is 7 times 10 to the 19th. This iron EDTA is, the equilibrium constant is 1.7 times 10 to the 34th. Right? And this zinc cyanide equilibrium is, the equilibrium constant is 2.1 times 10 to the 19th. Right? So these have very large values of the equilibrium constant. That gives us a different opportunity in terms of the kinds of calculations we can do. All right, let's consider this reaction where we're forming that zinc tetracyanide ion. And let's consider a system where we start out with 0.05 molar zinc in our solution, 0.08, and let's add a significant figure just for fun, 0.080 molar cyanide ion, right? And 0 zinc cyanide, right? How do we deal with this when we have a very large equilibrium constant? Well, one thing we can do is first treat this reaction with a large equilibrium constant as if it's going to go to completion, right? So first, think about treating this like a complete reaction, which means treating it like a limiting reactant problem, okay? So if we're going to treat it as a limiting reactant problem, we have to figure out what our limiting reactant is. It ends up, right, if you go through here, the limiting reactant is going to be the cyanide, right? Because if we react all of our cyanide, we will only react a little bit of our zinc ion, right, because of the 4-to-1 stoichiometry, which means we will make 0.020 of our zinc tetracyanide complex ion, right? And so after we get done considering the complete reaction, we have 0.030, 0, and 0.020, right? Now we can take that as the initial point for our equilibrium, right? Now we can treat this as an equilibrium system again, right? Since if we look at our change, since we have no cyanide ion, we have to make some cyanide ion. The only way we can do that is by dissociating some of our zinc tetracyanide complex ion. That will make 4x of our cyanide ion and x of our zinc ion. And so when we reach equilibrium, we will have 0.030 plus x, 4x, 0.020 minus x. But this is a very large equilibrium constant. We would expect our equilibrium to stay very far toward products, and maybe then for these x's to be negligible, right? So we can try that estimate. And so we have our K, our equilibrium constant, is going to be the concentration of our zinc tetracyanide ion divided by the concentration of zinc ion divided by the concentration of cyanide ion raised to the fourth, right? So that's going to be 0.020 divided by 0.030 times 4x to the fourth, and that's going to equal the 2.1 times 10 to the minus 19. Right? So if we multiply both terms by this and divide both terms, both sides by this, we can get an expression that looks like this. That let's change colors here so we can read it a little better. 0.020 divided by 0.030 times 2.1 times 10. Oop, and I almost messed up here, right? We have to remember, right, we're dealing with big equilibrium constants, not small ones, right? We get so used to putting that negative exponent on there, we got to remember to pay attention. That's 10 to the 19th. That's positive, right? Is going to equal 4x all raised to the fourth power, which is going to equal 256 x to the fourth. Right? So we're running out of space a little bit, but we'll have our 0.020 divided by 0.030, 2.1 times 10 to the 19th, and divide by 256 equals x to the fourth. Right? X to the fourth is going to equal 1.24 times 10 to the minus 22. If we take the fourth root of that, we will get that x equals 3.337 times 10 to the minus 6 molar, right? And so then we can find, right, our concentration of cyanide would be 4 times that, right? So the concentration of cyanide ion when we reach equilibrium will be 1.335 times 10 to the minus 5 molar, right? And so then, right, these concentrations would be very close to that with a very small error, right? So when we're dealing with reactions with very large equilibrium constants, right, we first pretend it is a complete reaction and work the limiting reactant problem. Use the endpoint of that limiting reactant problem as the start for our equilibrium. And then if the equilibrium constant is very large, most of the time we can make our assumption to simplify our calculations to find out what the equilibrium concentrations are at the end of the problem. Okay, so let's do a quick review problem, right? What is the solubility of silver chloride in pure water if the KSP for silver chloride is 1.77 times 10 to the minus 10, right? So we know, right, we look at our setup, our ice table, right? We've got silver chloride solid in equilibrium with silver ions in solution. and chloride ions in solution, right? Our initial is, right, we need solid, 0, 0. Some little bit of that solid will dissolve and dissociate to make X of that and X of that, since I picked a nice salt that is 1 to 1. And so at equilibrium, we still have to have solid left. We're going to have X of that and X of that. And so our 1.77 times 10 to the minus 10 is going to equal, right, our silver ion concentration times our chloride ion concentration, right, since the solid silver chloride has an activity of 1, right, and so that's going to be 1.77 times 10 to the minus 10 equals X times X. So 1.77 times 10 to the minus 10, the square root of that is equal to X, which is equal to 1.33 times 10 to the minus 5 is equal to X, right? So the solubility is 1.33 times 10 to the minus 5 moles of silver chloride will dissolve per liter of pure water. Okay? Nice review problem. All right, let's consider a slight change. All right, so let's look at this slight variation. What's the solubility of silver chloride in a 0.25 molar solution of ammonia? Now, we're going to be given two things. Ammonia and silver ions form a complex ion, a silver diammonia complex ion. And the formation constant for that is 1.7 times 10 to the 7th. And then the KSP for silver chloride, right, the solubility product constant, is 1.77 times 10 to the minus 10, right? And so let's look at these two reactions, right? So let's consider our dissociation of silver chloride, right? So we've got silver chloride, solid, in equilibrium with silver ions, aqueous, plus chloride ions, aqueous, right? And if we consider our formation of our complex ion, we've got silver ions, aqueous, plus 2 ammonia, aqueous, in equilibrium with this silver ammonia complex ion, right? Now, one of the things we can do if we have two equilibrium reactions that share components, right? Silver is a product here, and it's a reactant here, right? Silver is a product here, it is a reactant here. And so if we simply add those together and then eliminate like what appears on both sides exactly, right? So we end up with a combined reaction that is silver chloride, solid, plus 2 ammonia, aqueous, would be in equilibrium with silver diammonia complex ion, aqueous, plus chloride ion. Right? We get a combined reaction. And to find the equilibrium constant for those, we just multiply the two equilibrium constants together. Right? We multiply our, let's go this way first, our KSP, the equilibrium constant for the first reaction, times our formation constant. And so let's look what that would look like, right? So our KSP would be the concentration of silver ions times the concentration of chloride ions. And since silver chloride is solid, that would be 1, right? Our formation constant is the concentration of silver ammonia complex ion divided by the concentration of silver ion times the concentration of ammonia squared, right? Because of the 2 there. If we go through, silver ion divided by silver ion is 1, right? Now, I don't really have room here, but I think you can see, right? We're going to have, right, our bottom equilibrium, concentration of chloride ion, concentration of chloride ion. Maybe I can fit it in here, right? Concentration of silver ammonia 2 times the concentration of chloride ion divided by the concentration of ammonia squared, which would be the equilibrium constant for that reaction that we have expressed right there. Right? So if we have 2 linked reactions, we can find the equilibrium constant for the overall reaction by multiplying together the equilibrium constants of the individual reactions. And that works for any kind of linked equilibrium. But for us now, it works very nicely because now we can take our 1.77 times 10 to the minus 10 times our 1.7 times 10 to the 7th and get an overall equilibrium constant of 3.009 times 10 to the minus 3. Now we've got a more straightforward equilibrium constant and equilibrium situation we can work. Now we can find the answer to our question. So here we've rewritten that equilibrium, right? And let's look at our initial condition, right? We want to have some solid silver chloride. We said we were going to use 0.25 molar ammonia. We've got no silver ammonia complex ion, no chloride ion. And just to remind ourselves, right, we found out that our equilibrium constant for this was 3.009 times 10 to the minus 3, right? Okay, so, right, if we look, we've got to create some of this, right? Let me make my pen just a teeny bit bigger, right? We got to make some of that, and we got to do away with 2x of that. We're going to do away with x of that, right? That's fine. So when we reach equilibrium, we should still have solid, right? We're looking for solubility, right? So we want to make a saturated solution. We're going to have 0.25 minus 2x. We're going to have x, and we're going to have x. And so our 3.009 times 10 to the minus 3 is going to be equal to x times x, right, our products, divided by 0.25 minus 2x all squared. Now, I know you're looking at me going, oh, are we going to run into the quadratic? But, right, we have to remember that situation that we can run into, right, where both The numerator and denominator are squared, so we have a perfect square equation. So we can take the square root of both sides to simplify things. And so we get that 5.4854 times 10 to the minus 2 is equal to x over 0.25 minus 2x, right? Now we can multiply that through and get 1.37136 times 10 to the minus 2 minus 0.10971x is equal to x. So if we add this to both sides, right, we get 1.37136 times 10 to the minus 2 equals 1.10971x. So x is equal to 1.37136 times 10 to the minus 2 divided by 1.10971, and we end up getting about, to two significant figures, 1.2 times 10 to the minus 2, right? And remember, x then was the solubility in moles per liter, right? If we go back and compare that to what we got, right, in pure water, the solubility was 1.33 times 10 to the minus 5 moles per liter, right? So we're going from the range of 10 to the minus 5 moles per liter to 10 to the minus 2 moles per liter. So just adding 0.25 molar ammonia increases the solubility almost 1,000-fold, right? That's the power of those complex ions being formed, okay? So there's a lot in this. You need to practice these. There are problems at the end of the chapter that you should work to get comfortable with complex ion formation and how it can increase solubility of less soluble ionic compounds.